You know, when you see ancient pottery or these beautiful old tiles, you kind of think of ceramics as being immortal, right? But it turns out, even these incredibly durable materials have a hidden weakness, a slow molecular decay. So let's dive into how even the strongest ceramics can eventually fail.
So here's the big question. If a ceramic pot can survive buried in the ground for thousands of years, what on earth could possibly bring it down? And we're not talking about smashing it with a hammer or throwing it in a furnace. Now, the real enemy is way more subtle, and it's happening all around us all the time.
The answer is corrosion. But, and this is a big but, it's not the rust you see on a car. This is a whole different beast. Ceramics corrode through direct chemical attack. You've got acids or bases that literally just dismantle them, plucking them apart molecule by molecule. It's a completely different kind of decay.
Now, to really get this, you have to see a ceramic object as a war fought on two fronts. You've got the shiny, glassy outer layer, the glaze, and then you've got the porous ceramic body underneath it. And corrosion attacks each of these in fundamentally different ways.
So here's the battle plan. For the glaze, it's a surface war. Chemicals on the outside leach out ions and start to dissolve that glassy structure. But for the body, it's an invasion. Corrosive stuff actually sneaks in through a whole network of tiny pores and microcracks, and it starts attacking from the inside out. It's really the difference between a frontal assault and an infiltration mission.
So let's zoom in on that surface battle for a second. How exactly does a seemingly solid piece of glass or glaze get taken apart? Well, the science is actually fascinating, and it's been studied a ton, partly because it's the exact same process that affects the special glass we use to contain nuclear waste.
It basically happens in 3 stages. First up is ion exchange. Think of it like a bad trade. The glass has these weakly held sodium ions, and water comes along and swaps them for hydrogen ions. This trade-off weakens the whole structure right at the surface. Then, with those ions gone, the local pH right there on the surface changes, and that change starts to dissolve the strong silica backbone of the glass itself. And finally, some of that dissolved material can actually precipitate back onto the surface, creating a new layer that, if you're lucky, might slow down any more damage.
So after all that molecular action, what does this battlefield actually look like? Well, this is a micrograph of a corroded glass surface. It's not smooth anymore, is it? It's become this transformed, almost alien-looking landscape of chemical decay, and it's covered in these crystalline byproducts from the reaction.
Yep, that's it. That's the physical evidence of that 3-step process we just talked about. It's a perfect visual record of glass being taken apart piece by piece at the molecular level. So if we were to break down what we're seeing here, you've got these layers of damage. Right at the top, that's the precipitate layer, those new crystals. Just beneath that, you have what's called the transform layer. That's the original glass, but it's now chemically altered and super weakened. And then finally, deep below all that chaos, the bulk glass is still pristine, completely untouched. But here's the thing. All that fancy chemistry is only half the story. As this quote points out, the speed of the attack is really controlled by transport. I mean, it doesn't matter how aggressive a chemical is if it can't get to the material in the first place, right? So it's the physical pathways, the pores, the tiny cracks, the little gaps. Those are what truly dictate how fast the ceramic body is going to degrade from the inside. Okay, so knowing how it happens is cool, but in the real world, engineers need to actually predict and measure this stuff. I mean, how do you test a floor tile to see if it's going to stain, or a crucible to make sure it won't just fail while it's holding molten metal? Well, there are a few key methods. We can literally just submerge materials in strong acids and bases and measure how much weight they lose. For things like tiles, we test stain resistance, to see how easily coffee or wine can get into the surface. And for heavy-duty industrial ceramics, we test them against the most aggressive stuff imaginable, molten metal and slag. And believe me, the stakes here are incredibly high. For a refractory crucible like this one, corrosion isn't about a cosmetic stain. If this fails, you get a catastrophic release of molten metal. So these tests, they're not just academic exercises. They are absolutely critical for safety and for pretty much all of our industrial processes. So what's the big takeaway here? It's that if we understand how ceramics fail, we can actually design them not to. This knowledge isn't just about understanding the past, it's literally a blueprint for creating materials that can truly withstand their environments, potentially for centuries. And here's how you do it. First, you strengthen the glaze's chemical backbone with more silica and alumina. Then, you cut way back on those easily leached alkali ions. You have to control the firing process perfectly to prevent weak spots from forming. And maybe most importantly, you create a dense, perfect surface to seal off any and all pathways for those corrosive chemicals to get in.
And that brings us to a final, much bigger thought. We've just walked through the science of making a simple glaze incredibly tough. And it makes you wonder, if we can do that for a glaze, what other materials that we think of as permanent could we re-engineer at a molecular level to be truly, genuinely timeless?